I will tell singer Lata Mangeshkar passed away yesterday. She will remain an eternal shining star in the world of music. And she will remain in our heart in every moment. She was Goddess Saraswati to all of us. And as a Bengali, this is our proud. Lata Mangeshkar said, Swami Vivekananda inspired her throughout her life. She also devotees of Ramakrishna Paramahansa Thakur. Oh, may she rest in peace and light up heaven with her brightness. Welcome back. In my earlier video, I had discussed about correspondence theorem of ring with some example which had come in CSR net. Today I will discuss some important question of CSR net based on maximal ideal, prime ideal and PID. The question had come CSR net 2020 November exam. The question is, let R and S be commutative ring with unity and F be a mapping from R to S which is surjective ring homomorphism, and Q subset of S be a non-zero prime ideal. Then which of the following statement are true? Option 1, F inverse Q is a non-zero prime ideal in R. Option 2, F inverse Q is a maximal ideal in R if R is a PID. Option 3, F inverse Q is a maximal ideal in R if R is a finite commutative ring with unity. And option 4, F inverse Q is a maximal ideal in R if x to the power 5 equal to x, where for all x in the ring R. Okay? At first say the first option. Here we have to prove F inverse Q is a non-zero prime ideal in the ring R. Here just at first say F is ring homomorphism. Here not only ring homomorphism, it is the surjective ring homomorphism, and given Q subset of S be non-zero prime ideal. Now the all option given about the F inverse Q, at first see what is the F inverse Q in the ring. F inverse Q means set of all R in the ring R such that F of R belongs to Q, where Q be a non-zero prime ideal. At first we have to prove this set F inverse Q is a non-zero prime ideal. For this, at first we have to prove F inverse Q is a ideal in the ring R. And obviously this should be subset of the ring R. Now consider two arbitrary element R1, R2 belongs to F inverse Q. Okay? Then F of R1 minus F of R2 by the property of ring homomorphism, this is equal to F of R1 minus F of R2. Okay? And obviously F of R1 be the member of Q and F of R2 be the member of Q. Because R1, R2 be the member of F inverse Q, and since given Q be a non-zero prime ideal, then obviously their difference means F of R1 minus F of R2 belongs to the set Q. That means from this line we can tell R1 minus R2 belongs to F inverse Q. Now I will prove the second condition of ideal. Consider RB arbitrary element of the ring R and consider R1 be the member of the set F inverse Q. To prove ideal, we have to see R times R1 belongs to F inverse Q. For this, consider F of R times R1, and by the property of ring homomorphism, we all of us know this is equal to F of R times F of R1. Okay? And since R be arbitrary element of the ring, so obviously F of R be the member of S, because the mapping is denoted as F of R to S, and F of R1 would be member of Q. But since Q be non-zero prime ideal given, so obviously from this line we can tell this is member of Q. That means our proof has done. R times R1 belongs to F inverse Q. Okay? That means second condition of ideal also has satisfied. That means this set obviously be ideal in S. In R. How I will prove this set be prime ideal? For this, let A and B belongs to ideal, and here given the ideal I equal to F inverse Q. Okay? That means from this line we can write it is easily F of A, B belongs to Q, and since Q be non-zero prime ideal, so from this line, by property of ring homomorphism, we can write it as F of A times F of B belongs to Q. And since given Q be non-zero prime ideal, so obviously either F of A belongs to Q or F of B belongs to Q. Are we getting the idea? That means either A belongs to F inverse Q or B belongs to F inverse Q. So, obviously, since here I equal to F inverse Q, that means our proof has done. The set F inverse Q is a prime ideal in the set R. Okay? And in the question has indicated this I be non-zero prime ideal. Just think how this is possible. Because if I means F inverse Q equal to singleton set 0, then that imply under the mapping, obviously it mapped to 0. But this is the set. F of 0 belongs to Q. But here in the question indicate Q be non-zero prime ideal in the set S. So obviously this ideal F inverse Q be non-zero prime ideal. That means our proof has done. First option B, right option. F inverse Q be a non-zero prime ideal in R. Second option given. F inverse Q is a maximal ideal in the ring R if R is a PID. And this option obviously true, we all of us know, because we all of us know in PID every non-zero prime ideal be maximal ideal. Since here given R is a PID and I have proved few minutes ago F inverse Q be non-zero prime ideal. So obviously F inverse Q is a maximal ideal in R. Okay. So option 2 is also right option. And third option given, F inverse Q is a maximal ideal in R if R is a finite commutative ring with unity. There is also nice theorem. If R is a finite commutative ring with unity, then maximal ideal always imply prime ideal, and this condition is if and only if condition. That means prime ideal also imply maximal ideal and maximal ideal imply prime ideal. Are you getting? That means option third is a right option. F inverse Q is a maximal ideal in the ring R if R is a finite commutative ring with unity, because I have proved F inverse Q is a prime ideal. And since here given R is a finite commutative ring with unity, so obviously this option is the right option. And option 4 indicate F inverse Q is a maximal ideal in the ring R if x to the power 5 equal to x for all x in the ring R. Okay. Now let's see the proof for this option. For this condition x to the power 5 equal to x for all x belongs to R, if we can to prove R modulo I be a field, so obviously we all of us know the ideal I be maximal ideal. For this, let's consider R bar, which is equal to R plus I, be non-zero element of R mod I. So, for this, consider R plus I to the power 5, which is equal to, by the property of ideal, this is equal to, we all of us know, R to the power 5 plus I, and here in condition we can write it easily. R to the power 5 means R plus I. Therefore, R plus I means, we all of us know, R bar. Okay. Therefore, I have got R bar to the power 5 equal to R bar. Where? For all R bar not equal to 0. And from this line, we can tell easily R bar times R bar to the power 4 minus 1 equal to 0 bar. Since I be prime ideal, so obviously R mod I be integral domain. So R bar times R bar to the power 4 minus 1 equal to 0 bar imply either R bar equal to 0 or R bar to the power 4 minus 1 equal to 0 bar. Sorry, here also 0 bar. Since all R bar not equal to 0, so this is not possible. Only possible R bar to the power 1, R bar to the power 4 equal to 1. Here actually would be 1 bar. And from this line we can tell easily R bar times R bar to the power cube equal to 1 bar. So I have chosen R bar be any non-zero element of R mod I. So from this line we can tell every element has an multiplicative inverse. Are you getting the idea? Since every element has multiplicative inverse, that means obviously this quotient ring R mod I is a field. Okay? Well, that means option 4 is a right option. F inverse Q is a maximal ideal in R if x to the power 5 equal to x for all x in R. This is very important option. That means this is also right. Now let's see other example which had come CSR Net June 2015 exam. This question is easy type of question because we have discussed this type of question in my earlier video elaborately. Just recall this question again, once more again. The question is, just look, let C01 be the ring of all real valued continuous function on the set 01. Then, which of the following statement are true? Option 1, C01 is an integral domain. We all of us know this is the wrong option because I had seen in my earlier video in C01 means obviously set of all function which is defined from 01 to r which is continuous. If we consider the function as this type fx equal to 0 on the interval 0 less than equal to x less than equal to alpha and from alpha to x less than equal to 1, the value of the function is x minus alpha and gx equal to x minus alpha in the interval 0 less than equal to x less than equal to alpha and 0 in the interval alpha less than x less than equal to 1. Obviously, this is the graph of the function. Obviously, this function is defined on the interval 0, 1. Obviously, the function f, the graph of the function f is just this type of function. And notice the function is defined in the interval 0, 1 and this function is obviously continuous function on the interval 0, 1. Here, in the interval from 0 to alpha, the value of the function is 0 and alpha to 1, the value of the function is x minus alpha. And gx would be this type. This is the g function. I have discussed this function in my previous video elaborately. From this function, we can tell easily fx times gx would be equal to 0. But neither f is 0 function nor g is 0 function. That means I have got a function in C01 which contain divisor of 0. That means obviously C01 is not integral domain. And option 2 indicate set of all function vanishing at 0 is a maximal ideal. We all of us know in C01 the function f of a equal to 0 where a belongs to any number, any real number, obviously be maximal ideal. I have discussed this part in my earlier video elaborately. Are you getting why I have told you this type of question is very important for any competitive exam? By this method, you can easily tell the set of all function which is vanishing at 0 is a maximal ideal. But here I have also seen set of all function which vanishes at 2 point. This is not be maximal ideal. Only maximal ideal be set of all function which vanishes at the point. Here consider the function is vanishes at the point 0. Here the point is a is 0. That means here f of 0 equal to 0. Okay. For this, here I will use another method. Here C01 and consider the ideal I0 equal to f belongs to C01, f of 0 equal to 0. Now consider a ring homomorphism phi from C01 to R such that phi of f equal to f0. I have seen in my earlier video this is onto ring homomorphism and kernel of f equal to I0. Therefore, by first ring isomorphism theorem, we can tell C01 modulo I0 is isomorphic to real number. Okay? This is the other method. And we all of us know this theorem. If R is a CRU, that means commutative ring with unity, then R mod I is a field. If and only if I is a maximal ideal. And since R is a field, so obviously this ideal means here this ideal be maximal ideal. Are you getting the other method? Okay. And option third, indicate the set of all function vanishes at 0, 1 is a prime ideal. We all of us know this type of function not maximal, not mean prime ideal. This type of function I have defined in my earlier video also. Just see here, the point is defined as vanishes at the point 0 and 1. The function is vanishes at the point 0 and 1. So consider the function is look like f belongs to C01 such that f of 0 equal to 0 and f of 1 equal to 0. Then consider the function x and 1 minus x. Obviously x times 1 minus x belongs to this ideal. Just look, but notice neither x belongs to I naught nor 1 minus x belongs to I naught. That means I have got AB belongs to I naught, but neither A belongs to I naught nor B belongs to I naught. So obviously this ideal not be prime ideal. Are you getting? OL. That means option 3 also wrong option. And option 4 indicate f belongs to C01 is such that fx to the power n equal to 0 for all x belongs to 01. And that implies fx equal to 0 for x belongs to 01. This is trivial case. This option always true. This, let's see again. Given f belongs to C01 such that fx to the power n equal to 0 for all x belongs to C01, where C01 be the set of continuous function on 0, 1 to r. And fx to the power n equal to 0 means fx times fx n which is equal. And fx to the power n equal to 0 means we all of us know fx times fx here n times equal to 0. And from this line we can tell obviously this is equal to 0 mean obviously this would be fx equal to 0. That means option 4 obviously right option. Are you getting? Okay.